So today we're going to talk about VSEPR theory. VSEPR stands for valence shell electron pair repulsion. And to break that down a little bit for you, valence shell just talks about the electrons in the outermost shell because those are the ones that do the bonding and those are the ones we care about. We're going to look at electron pairs because we know that electrons, if you think of an orbital diagram, like to be in pairs, a spin up and a spin down. We're still looking at pairs. And repulsion talks about how when you have a pair of electrons, they are going to repel other electrons within the same compound. So repulsion is when you have two of the same charge and they are pushing away from each other. So what is VSEPR theory? It's actually a model that predicts the shape or geometry of molecules based on two things, the number of electron pairs on the central atom and the number of bonded atoms to the central atom. So what we're going to do is take a look at some Lewis structures that have been done for you, and we are going to take a look at the 3D sketches of what those would look like. So the first one we're going to look at is carbon dioxide. What you'll notice is that carbon dioxide has two atoms bonded to its central atom. So that's where we get 2. And then we have 0 electron pairs on the central atom. There are pairs of electrons on the bonded atoms, but we don't really care about those in terms of what the shape of the structure is going to be. So we're going to put an atom in the center that represents the central atom and carbon in this case, and we're going to draw bonded atoms that are labeled A to represent those atoms that are bonded. We're just drawing a general structure to help us to generally see what the shape of any atom with this Lewis structure would be. This is called linear because all of the atoms are in a line, and you will see the 180-degree bond angle between the two bonded atoms. If you wanted to see what a picture of this would look like, here is an example of a linear structure using the ball and stick model. The ball represents the atom, the stick represents the bond between the atoms. So then we can look at another structure that is called bent. And this structure has, it actually has 2 bonded atoms, just like the linear, but this one has one pair of electrons on the central atom. And then we've got our 2 atoms bonded. So when you have a structure that looks like this, a Lewis structure, you're going to take your central atom in the middle, and because of that lone pair of electrons on the top, your bonded atoms are going to get pushed down a little bit. So what you can't see in the shape is the lone pair of electrons that are on the top. And we draw a big circle around it to represent the space that it's going to take up. So we're pushing down on that electron pair, and that gives us this bent shape. The angle between the 2 atoms is going to be 120 degrees. And if you wanted to see a structure of what that would look like, you see these here. These represent the bent shape. So you have the 2 bonded atoms and your lone pair of electrons on top, and then technically you cannot see the electrons. So what the actual shape of the structure would look like is just this bent looking shape with 120 degrees in between. Then you could take a look at SO3, which is going to be something called trigonal planar. And what that's going to look like is you're going to have your central atom in the middle, and each of the bonded atoms is going to be as far away as it can get from the other bonded atoms inside the molecule. So we have 3 bonded atoms and 0 lone pairs on that central atom. So you notice there's nothing on the central atom with sulfur. And then if you go around in a circle, the largest bond angle that the way that you can get the atoms farthest apart from each other are going to be 120 degrees. So that is our bond angle for trigonal planar. And that structure is going to look like this, where if you were to connect the dots between the three bonded atoms, you would get a triangle, hence trigonal planar. If you flip the page, you will take a look at our next Lewis structure, which is of methane, or CH4. And this structure is going to have 4 bonded atoms. And again, we're looking at 0 unshared electron pairs. So with this structure, in order to get the atoms all as far apart from each other as we can, they're going to get, we have our central atom actually, the C in there. And it's going to kind of look like a tripod on the bottom. So these guys are going to go on either side, and then there's going to be one that kind of comes out in the front like that. And it's kind of hard to represent this in a 3D way, so I'll show you a picture. And then there's one little guy that comes up off the top. So there's 4 of those hydrogen atoms coming off, and they're all about as far away from each other as they can get, being distributed evenly around the circle, or around the carbon atom or the central atom. So in this case, the largest bond angle is going to be 109, or 109.5 actually, degrees. And this is called tetrahedral. It should be easy to remember that it's tetrahedral because hedral means sides, and tetra means 4, and there are 4 bonded atoms. So H2O has 8 valence electrons. This is the structure we're going to get. We have 2 atoms bonded to the water molecule, and we have 2 lone pairs of electrons. So our structure for this, we're going to have our central atom, and we're going to have the bonded atoms coming off the bottom. This looks a lot like the other bent structure that we saw before, where you're going to have a bond angle of 104. So it's a little bit smaller. They push because there's 2 lone pairs of electrons pushing off the top of that central atom, they're really pushing hard on those bonded atoms to push them down closer to each other. Those electron pairs are going to take up so much more space. So this is bent 104, just to clarify which one is which. And I realized I didn't show you your tetrahedral. This is what a tetrahedral would look like, just like CH4, where you have your central atom and you've got this little tripod coming out with one guy sticking up in the top. And then the water molecule would look something like this, where you have your central atom, and it looks just like the other bent structure. It's just that the angle between the 2 bonded atoms is a little bit smaller. We've got 2 more to go. We've got ammonia, which is NH3, and we have our 1 pair of lone pair at the top of the central atom, and we have 3 bonded atoms on our compound, and we're going to put our central atom in the middle, and we're still going to have that same kind of tripod structure that we had with the tetrahedral, because this lone pair of electrons again is pushing everybody down and taking up the most space. So there is an angle of about 109.5, again, just like the tetrahedral structure, 109.5 degrees. This is called trigonal pyramid. So the reason that it looks similar to the tetrahedral is because it is just like the tetrahedral. There are 4 places where electron pairs might be. It's just a difference between which ones are bonded and which ones are lone pairs. So this structure looks, I know it's a small picture, but it looks like this, where the yellow represents a lone pair of electrons, and what's left over, the white, are the bonded atoms. So it's literally going to look like a tripod without without anything on top of it, like the tetrahedral one would have. And then finally, we have PF5 phosphorus pentafluoride, where we have 5 bonded atoms. And remember, this is okay for phosphorus to have 5 bonded atoms because it is in the 3rd row of the periodic table, where the elements start getting a little bit larger. And I'm actually going to draw this picture a little bit further down on the page because it's going to take up some space, and I want to show you some different things about it. So we're going to have our central atom here, and we are going to have a bonded atom coming off the top here. The whole goal of this is to get as many atoms as far away from the other atoms as possible. And then we're going to have one coming down like this. So there are 2 different bond angles here. We're going to have a bond angle between all of these atoms at 120 degrees. It's kind of like a Mercedes-Benz sign where you have just cut this circle into 3 different parts, and the angle between them would be 120 each. And then the bond angle between the top and bottom atoms and their nearest neighbor up here is going to be 90 degrees. So basically you have something like this, and they're coming out like that, and then something down here like that. So there's right angles in between the ones that they're basically perpendicular to each other. So this structure is called trigonal bipyramid. And it's easy to get this one mixed up with, or bipyramidal. It's easy to get this one mixed up with the trigonal pyramid or the trigonal planar, or not trigonal planar, but just the trigonal pyramid, because one's a pyramid and one's a bipyramid. So the pyramid would make a pyramid with a triangular base. So you get something like that. Whereas the trigonal bipyramid still has the triangular base, but now it actually creates kind of like a diamond in a way, where you end up with something that looks like this. And I'm not the best artist here, but you have that triangular base, and then there's a pyramid on top and a pyramid on the bottom as well. So that structure is really hard for me to draw. If you have space, you can put that right in there. But so what that structure is going to look like is this. So you have this triangular center, and then if you were to draw lines connecting each of the outer atoms or the horizontal atoms to the tip of it, you would create this pyramid structure. And then the same thing happens on the bottom. So that's what the structure would look like for a trigonal bipyramidal molecular geometry. So we've gone through all of these. If you have any questions, feel free to send me an email, or I can always share with you some of the other videos that different people put up around on the internet if you need a different perspective. Otherwise, go ahead and for homework, complete all of the questions on page 43 in your packets. Okay, good luck.